The last type of renewable energy that we're going to look at is solar energy. There's actually two systems here that we need to be aware of for harnessing solar energy, so we'll deal with them separately. The first one is solar heating panels. Now, for solar heating, it's basically just another sort of form of thermal energy transfer, and in this case, infrared radiation from the sun. So dealing with internal energy, basically. Infrared radiation from the sun heats up water. And that water is contained in pipes. Usually you'll find it sort of on the roofs of homes or buildings. And those pipes generally are located in black panels. So black being the colour that absorbs the most energy from the sun. So it's the most efficient transfer of energy. So that heated water is then pumped through a heat exchanger, and can be used for a few different things. By pumping it through a heat exchanger, it allows the thermal energy from the heat exchange to be used by consumers. So thermal energy from the water to be used by consumers. And again, to help you make sense of this, here's a diagram of a solar heating panel. So you can see on the right here we'd have infrared radiation on the solar panel itself, represented as the black panel. So these yellow lines here would be the pipes that are located in that black panel. You can see there that we've got cold water coming in, hot water then coming out. There is a pump there that allows that water to be controlled, how fast it's flowing in and out. You can see there that water from the panel then gets transferred through the heat exchanger at the bottom. That it is then transferred to internal energy of another flow of water up the top. That can then be used for, say, just for hot water from taps or from out showers as well. So most commonly these sorts of systems are basically just used for hot water systems. The second type of system that we need to be aware of for solar energy is photovoltaic cells. Now, photovoltaic cells are the ones that you more commonly see on the roofs of houses, and they're more about producing electricity. So the solar heating panels, they're used, but they're certainly not as common as photovoltaic cells. Now, this one's a little bit trickier considering that we haven't gone through semiconductors. So some of the explanation here won't really be in enough detail compared to give you a full understanding of what is actually happening in a photovoltaic cell, but it's enough for the purposes of the IB course. So in a photovoltaic cell, we've got two types of semiconductors, a p-type and an n-type. Now, those types are basically they're the same substrate, so usually they'd be, say, a silicon semiconductor, but one would be doped so that it has extra holes, the other is doped so that it has extra electrons. So the p-type has extra holes that can carry charge, the n-type is extra electrons. The charge in them both, though, is actually still neutral. It's what they're doped with still is a neutral atom, and so each of those is still neutral in each layer. When we then have photons of light from the sun striking those layers, they can displace electrons. So photons strike the semiconductors, we end up seeing electrons being displaced. And if electrons are displaced, that means that we start to form a charge separation, or causing an imbalance of charge. And as we know, whenever we have an imbalance of charge, if we have a lack of charge in one area and an excess of charge in another, that means that we're going to see an EMF, and in this case we'll also then see a small current as well. And that small current is actually through an external circuit. So by using sunlight displacing electrons, we can then convert that solar energy into electrical energy. So that's one of the key differences between the two systems. So here we're seeing solar energy being converted into electrical energy, whereas in the solar heating panels, it's basically solar energy being converted to internal energy. Each cell, though, generally speaking, only produces a small EMF. So each cell being a PN junction, so P-type and N-type. So with each cell, only produces a small EMF and a small current. It usually means that we'll have banks of cells joined together. And those banks of cells joined together in a panel, and quite often you'll see that you need a number of panels in order to produce enough electricity. So when the banks of cells are joined together in a panel, first in series connections and then in parallel. So by placing them in series, it means that we can increase the EMF, and by placing them in parallel, it means that we can produce more current for a longer period of time. So that's basically to optimize both voltage and current. And when we optimize the voltage and current, we're also going to minimize power losses. If we consider both of these, there are some benefits that both systems provide. And the first is that they have low maintenance costs. So once they're installed, they're generally pretty straightforward to run, and don't usually need all that much in terms of maintenance. They also have no fuel costs, so we don't actually need to buy gas bottles or anything else to in order to have these systems running. And on top of that, individual households can use them. So while we do have some large solar arrays to produce power in some countries, it's probably even more beneficial than most sources in that individual households can make use of both of these systems. On the flip side, there are some downsides. First is that the installation cost is quite high. So you've got first of all the production of the panels themselves, and so you've got that cost, and then the large installation cost as well. So it requires a bit of effort to actually install them on top of houses, and they are also fairly inefficient compared to other sources. So they're their efficiencies are quite low. However, in the case of using them in a house, if you can offset some of your electricity bill by producing your own solar, while it might be low efficiencies, you're still able to produce some of your own energy. And the final thing too there is that the outputs of both systems also depend on time of year and the weather. So when we're talking about the time of year, we're more specifically talking about the seasons. So we get more sunlight in summer, so more opportunity to convert solar energy there, and less in winter. And likewise with the weather, if it's particularly cloudy, then it means that the amount of solar energy that can be converted is far less, because a lot of that energy is being absorbed by clouds instead. So that's the end of the look at solar energy. We'll then move on to 8.2.